Hello, my name is Lauren Majeski, and I will be presenting my experiment entitled Shedding Light on Energy Quantization. So for a quick outline, I'm going to start with an introduction in this presentation with my goals for the experiment, and then the experiment itself will actually be broken up into three parts, being the speed of light, blackbody emission, and line spectrum emission. I'll discuss these parts individually, but I'll also have a overall conclusion at the end. So the goals of this experiment are to understand the nature of light and show the quantization of electronic energy levels. We accomplished this through three different experiments, determining the speed of light, analyzing blackbody emission, and obtaining the line emission spectrum for hydrogen and deuterium. So the first part is the determination of the speed of light. We use this oscilloscope here on the left to obtain an outgoing and a returning pulse for a laser beam reflected off of a mirror. And then we can determine the time difference between these two peaks using the oscilloscope. So this is a general schematic of the beam path, obviously not drawn to scale, but we have our laser going to the beam splitter to get the outgoing pulse, and then the beam is reflected off of the mirror to a focusing lens back to the detector. This is our data compiled for the speed of light results. We have the distance the beam traveled, the time from the oscilloscope, and then our calculated speed of light in meters per second. We can see that the data is more accurate for farther distances. So if we were to repeat this experiment, we would want to do more trials at greater distances. But when we average our results, we get a speed of light of 2.8 times 10 to the 8th meters per second. And this result will be used in all future parts of this experiment for the speed of light. So moving on to part two, blackbody emission. For a quick little background, a blackbody emitter gives off radiation in a range of wavelengths when heated, and this range changes with temperature. So the sun is a very classic example of a blackbody emitter. In this experiment, we collected the ultraviolet visible spectra of 3 light bulbs using an ocean optics spectrometer and a fiber optic cable. The 3 sources are an incandescent light bulb, a LED light bulb, and a fluorescent light bulb. So my first hypothesis was that the incandescent bulb will most closely follow Planck's model for blackbody radiation out of the 3 bulbs, since it is a true blackbody emitter that gives off radiation in a range of wavelengths when heated. So we are going to model our spectra in 2 ways. First is using Wien's equation to calculate the temperature of the sources, and this relates the maximum intensity wavelength of the source to its temperature, using B, which is Wien's proportionality constant. Secondly, we're going to use Planck's equation, which models the intensity, and this includes Planck's constant H. And this equation is important because it introduced the idea of the quantization of energy. And the way that we modeled this is we adjusted the intensity relative to the intensity of each source, and then adjusted the temperature to find the best fit of Planck's equation in order to determine the source temperature. So this is the spectra for each of our sources. We can see that hypothesis 1 is supported because the incandescent does mostly closely follow Planck's equation. And that's because as the bulb is heated, the emission profile moves into the visible region. We can see the LED and the fluorescent do not follow the continuous spectrum of blackbody radiation, and that's because these are not true blackbody emitters. LED combines different color lights to get white light, and same thing with fluorescent. You can see these distinct peaks, which is not characteristic of blackbody radiation. We also analyze solar data. So on the right here, we have data from Earth's outer atmosphere, and this very closely follows Planck's equation. This is the best fit for Planck's equation, and this is evidence for the quantization of energy. On the left, we have ground level data also. This does not follow as closely simply due to the fact that the sun's radiation is lost in Earth's atmosphere before it hits the ground due to the ozone layer, filtering UV light, and also Rayleigh scattering. So here we have our tabled results for the temperatures of each source using Wien and Planck's equation. We can see that the sun, obviously at the outer atmosphere, is the hottest, and that is also the one that most closely followed Planck's equation. And while it may seem contradictory that we can have the quantization of energy with black body radiation, the continuous spectrum is possible just because of the sheer number of molecules. As we approach numbers like Avogadro's number, we can obtain that continuous spectrum. So moving on to the last part, which is the line spectrum emission, we used a monochromator to disperse light from the discharge lamp shown here to obtain the emission spectrum of hydrogen and deuterium. So this brings us to the second hypothesis, which is that deuterium will have a larger ionization energy than hydrogen due to its larger mass. So this is our obtained line emission spectrum. We can see that this is evidence for the quantization of energy because we have these distinct lines for each energy level transition, and the energy level transitions are labeled. When we zoom in on each of these transitions, we can see that there's actually two peaks, one corresponding to each isotope, the hydrogen and the deuterium. And we see that there is some broadening of the peaks. This is largely due to the Doppler effect and the motions of molecules. The thermal motions can cause some of the width as well as the Heisenberg uncertainty principle. So this is our table data for the line emission. The biggest thing to take away from this is that the deuterium is at a slightly shorter wavelength than the hydrogen. This is due to its larger mass. And we can also use this Rydberg equation, which is shown in the top right, to calculate the emission lines for one electron systems. This is not efficient for multiple electron systems because the electron interactions complicate the emission spectrum. But based on this equation, we can plot 1 over wavelength versus 1 over the principal quantum number squared for hydrogen and deuterium to obtain the Rydberg constants from the slope. And we obtain these slopes using the Linus function in Excel. So these are our experimentally determined Rydberg constants. We can also obtain these constants theoretically using Bohr's equation shown here, where mu is the reduced mass, E is the elementary charge, epsilon naught is the vacuum permittivity of free space, and H is Planck's equation, and C is our speed of light. So the reduced mass is calculated using the mass of the nucleus and the mass of an electron. So we have tabled our experimental and theoretical Rydberg constants. We can see for both cases that the deuterium Rydberg constant is slightly larger. And this makes sense because this constant reflects the strength of an interaction between the nucleus and the electrons. We expect it to be slightly larger for deuterium due to its larger mass. We can also use Bohr's equation to create this ratio of the Rydberg constants, and this helps us to solve for MD, which is the nuclear mass of deuterium, using the nuclear mass of hydrogen and the mass of an electron. So we can do that experimentally, and then theoretically, we expect the mass of deuterium to be roughly twice that of hydrogen. And lastly, we can use a special case of the Rydberg equation, where we consider an infinite energy level, which just shows that the electron is being removed completely from the atom. And this helps us calculate the ionization energy by relating the wavelength to the energy. We can see that the deuterium ionization energy is slightly larger for both the experimental and theoretical calculation, and this supports hypothesis 2, and makes sense because our Rydberg constants are larger and the mass is larger, so the strength of the interaction is larger. So for our overall conclusions for this experiment, we were analyzing the nature of light. So we were able to determine the speed of light to be 2.8 times 10 to the 8th meters per second. And we were also able to find evidence of the quantization of energy. We see that Planck's equation for black body radiation very closely matches experimental data, especially with solar data. And we can also observe discrete line spectra for hydrogen and deuterium that shows the quantization of these energy levels. And that concludes my presentation. Thank you for listening.